sent yesterday? Yes or no?
Yes, sir.
Okay, then I can go little fast, and I will go fast. So let me do that. We have to study these topics in this module. First part is about integrate wares and its model and issues. And second part is IO structures design. And first part can be referred from um, Rabe, chapter number 4 and 9. And for second part, no specific book, maybe Weste or some different books. Okay. So integrate wares, as you have seen, have various specification here like length, width, and thickness. T here, and H is the thickness of the oxide under it, maybe SiO2 or other material. So the certain uh, term is defined here, like sum of width and spacing is called pitch. See this S is this piece. S is the spacing between two line going parallelly. Here, this is the space. Yes. So sum of this width W plus H is called pitch up a line, up line. I mean, in a same level, say metal 1 or metal 2. The thickness of the width ratio, I mean, thickness to width ratio T by W. T is this thickness of the wear and W is the width, is called aspect ratio. And when one wear switches, say this one is switching, its effect will be, say it is carrying a clock, its effect will be on the second one or vice versa. So it happens due to the capacitive coupling. We'll discuss regarding this later on in details, how much effect will be there in terms of voltage value. So also this is called crosstalk. So the lines, various lines will be there in the metal lines, rather let me call level. This is the substrate or bottom level where you are going to make MOSFETs, like as I have shown here, N plus region, etc. or make the N MOSFET, and in the N well the MOSFETs will be making. So on top of that you will have silicon dioxide, okay, to isolate the top of it. You have the metal one layer, and then above that you may have again a SiO2 layer, and then again another metal layer may be there. So in this way metal layer will go up, maybe up to 10 metal layer are available nowadays in the new processes. Normally the bottom layers M1, M2, etc. are very dense with less width and obviously length also to connect the uh, nodes of the gates or to connect the transistors even. Okay, suppose in a NAND gate, two input NAND gate, you have the pull down network. So here drains, the source and the drain of these two MOSFETs has to be connected. That may be requiring one small metal wire, or maybe the output of one node may be required to be connected to the another one by another metal layer. So various metal layers are required, and since one big processor needs billions of transistors, so with only one metal layer if you try to connect, like as you can see in a printed circuit board of radio, television, etc., you will see that only one metal line will be there, copper metal line, to connect different components in the PCB. That way, if you go, possibly it will take a very big area. Say around 40 billion transistors are there. And if you want to connect all those with only one metal layer, it is going to take huge area, chip area. So that is not possible, because within small silicon area, chip area, you have to make big circuits. So multiple metal lines are used, and hence you can see here that this is a N plus region, possibly for an N MOSFET in a substrate, P-type substrate. And here is the via 1, you can say, bottom via, and one metal line is going there. This metal line is the bottommost one, maybe with mostly with aluminum, maybe also tungsten. But yes, obviously this via, this hole is made through the silicon dioxide and it is filled, and material is tungsten here at the this via, first via here at the bottom, and other vias at the top is only with aluminum, Al, and these metal lines also mostly of aluminum, metal 2, metal 3, etc. Okay, here is another view of the same thing. Say N plus region for N MOSFET, and this is poly. Under that, there is a very thin oxide layer. It is very thin, so it is not very clearly observable. Okay, and this is your P-type substrate, and see that multiple holes and vias are made, so that there is no chance of misconnection. Okay, with metal 1. If say only one contact you have made, if that is failing, means while filling the hole, complete connection is not made. You know how this metallization is done or filling is done? By CVD, chemical vapor deposition. It will be, metal will be in the evaporated form and it will be deposited gradually on the hole. So while filling the hole, it may not be perfectly made. So to avoid that, multiple via is made, and hence chance of that kind will be avoided. Metal 2 line you see here, and this way it will go up, metal 3, 4, 5, 6, even up to 10.
Sir,
Yes.
sir, every metal line is separated by SiO2?
Yes. In SiO2, maybe mostly SiO2, but nowadays some other material is also being used. I mean, other insulator. Okay. Reason behind that is you want to reduce the capacitance. Okay, between the two metal layers, you are putting the silicon dioxide. So this two metal layer is forming a capacitor, right? So if the dielectric constant is less, then capacitance will be less. C is epsilon 0 epsilon R A by D. So if this relative permittivity is less, dielectric constant is less, then capacitance will be less. Idea is to reduce the capacitance. So sometimes now from 130 nanometer technology generation onwards, SiO2 is being replaced by some other one. We'll see in the next few slides. Okay, you'll come to know gradually all these things. Understood?
Yes, sir.
You have to isolate, and definitely there'll be some oxide layer. Okay, whether it is silicon dioxide or other. Here is some properties of layers. Sheet resistance. You know, sheet resistance is what? Yes. Somebody is telling something?
Yes, sir. Sir, in the previous slide, can you repeat why we need maximum number of contacts?
See, suppose you have, previous slide, suppose you have one contact only, this one only for left side and this one only for right side, right? And
Yes,
you
sir.
don't have the other two contacts you are seeing here. Okay, it is not there, suppose. And while forming the or filling the hole, actually how we see from here to here, this much height, you have the silicon dioxide. It is not shown here, but it is there. So hole is made not by drilling, obviously, by etching. Okay, by etching process, different etching process is there. You can remove the silicon dioxide and make a hole up to this depth, and then that hole is filled with the tungsten at the bottom. In the bottom layer, this is the bottom layer, just above the silicon, substrate. Okay, this is filled with tungsten. The tungsten can withstand the high temperature processing. Upper metal, vias are filled with aluminum mostly, but bottom one is with tungsten. Anyway, so while filling, how it is filled? Chemical vapor deposition. This tungsten may be vaporized and it will be, its atom will be gradually settling on the holes. Not only holes, surrounding every area will be, also filled. A sheet of tungsten will be there. So once it is made, it has to be removed from other places, but this will be remaining there. The hole will be filled with tungsten. Is it clear? But while forming the hole, there may be a defect. There may be a defect. If defect is there, you are not able to make the contact with the N+ region here. Not here. This is the N+ region. This is a ground connection. Okay. Around the device and MOSFET, it is grounded. Okay, maybe for prevention of latch up, etc. Anyway, so point here is, if only one hole and the via is there, then possibility is there that connection will not be there. So to avoid that, multiple connections are shown around it, on top of it. Okay.
Yes, sir,
Understood?
Yes, sir.
Okay, let us go little fast. You might have seen all these things. Do you have any question in these slides? If I continue like this, then I'll take more time. So I don't want that. See, diffusion region, N+ region for N MOSFET and P+ region for P MOSFET have 3 to 10 sheet resistance. What is sheet resistance, by the way? Suppose one metal line is there. I have discussed, I think, and it is not drawn properly. Let me draw it properly. Suppose you have this metal layer, and if you divide it into a square, so it is this width of this is equals to 1, say, micrometer or so, or nanometer, whatever it is, and this is a 10 altogether length. L equals to this. So you are making squares, and every square is having some resistance. So if R square, it is denoted by square, R square is say 10 ohm. 10 ohm. R square is having a resistance of 10 ohm. Then total resistance will be how many? Say here it will be 10. L is 10 means 10 will be the square. So that much resistance you can calculate. We'll see the calculation of this interconnect resistance later on. But understand that the R square is the resistance of 1 square of that diffusion, or it is silicided diffusion, or unsilicided diffusion, or poly or metal one, etc. Is it understood, Prajual?
Sir, can you explain the difference between silicide and unsilicided?
Yes, this is going to come in future slides also. But remember that only diffusion, if you consider unsolicited diffusion, then you see here 50 to 200 ohm per square resistance is more. Whereas if you silicide it, then resistance is less, about 5 ohm per square. Per square resistance will be 5 ohm. What is silicided? It is a combination of some refractory metal like tungsten, cobalt, nickel, etc. Tantalum. This is called refractory metal because they can withstand very high temperature, right? And it is applied on diffusion or polysilicon, on the gate polysilicon. So if it is applied on polysilicon, then we say polysided, and silicided. This kind of terms are used. We'll see later on in details. That is the thing. Okay. So why it is done? To reduce the resistance of polysilicon or diffusion region. Understood?
Yes, sir.
Another metal, another table for metals, say silver, gold are having resistivity very less, say 1.6 micro ohm centimeter, gold 2.2 micro ohm centimeter, right? So those material should be used for interconnect, but it is too costly material, you know that, gold as well as silver. So normally that is not used. Aluminum is used. Metal 1 to metal 8 or 10. Okay, you will find that it is aluminum, not even copper. Why not copper? That has to be understood. Copper is there here. Copper is having less resistivity compared to aluminum. Still, aluminum is used, not copper. There are some difficulties in this copper. We'll study later on, which is called electromigration. Okay, that problem is there with copper, so aluminum was used. Nowadays, of course, processes are modifying. Copper is also being used with some precautions. Okay. So earlier interconnect inductance was not given importance and was treated as second-class citizen. It was not taken very seriously. It got importance in the era of DSM technology as device dimensions got reduced and circuit speed got increased. See how interconnects may be made in a chip. The wiring of today's ICs form a complex geometry that introduces capacitive, resistive, and inductive parasitics. All three have multiple effects on the circuit behavior, like an increase in propagation delay or equivalently a drop in the speed or performance. Then an impact on the energy dissipation and the the power distribution. Power line also ground and your VDD will be routed by this metal line only, but those are normally the top metal layers. Say if you have 10 metal layers, possibly the 10th metal layer at the top will be for VDD, ground, and clock signals. Okay, clocks are also routed with wider metal lines, and top layers are wider. Bottom layers are denser, and hence its width, length, and thickness are very less. And introduction of extra noise sources because of the capacitive coupling. This is one issue in the interconnect. Noise is occurring because of the interconnect capacitance coupling. One line is carrying some signal. Suppose this is carrying some signal, clock signal. This will be its voltage. Its voltage value will be changed. That is what crosstalk or capacitive coupling. See, a full-fledged circuit model taking into account the parasitic capacitance, resistance, and inductance of the interconnection is shown in this figure. Resistance, inductance, capacitance are shown. Some of the capacitance are grounded capacitance like this one and this one, but some of them are floating capacitances. Observe that these extra circuit elements are not located in a single physical point. It is distributed all over. But for demonstration purpose, we are showing as a lump capacitance or resistance. Fortunately, substantial simplifications can often be made, some of which are here. Some simplification can be made. Inductive effects can be ignored if the resistance of the wire is substantial. Means the line is very long, the aluminum line is very long. With a small cross section, the resistance will be more. Or if the rise and fall times of the applied signal are slow, then we can ignore this inductive capacitance. If you ignore that, then you may not show in the diagram, or you can ignore it in the analysis. When the wires are short, cross section of the wire is large, or the interconnect material used has a low resistivity, a capacitance model only can be used. Okay. Of that kind of interconnect, you can model it with only capacitance, ignoring resistance because it's short and diameter is more. Finally, when the separation between neighboring wires is large, or when the wires only run together for a short distance, so obviously capacitance will be less. Inter-wire capacitance can be ignored in such a case. An accurate modeling of capacitance wire or wire capacitance is a complicated task due to the fact that the interconnect structure of ICs is three-dimensional as demonstrated in this figure. This may be possibly the metal 1, metal 2, or metal 3. Maybe this is metal 2, metal 3, metal 4, etc. This may be the via. Okay. So capacitance of such a wire is a function of shape, its environment, its distance to the substrate, and the distance to its surrounding wires. So it is not easy to model. Exactly capturing the values of capacitance or resistance, particularly capacitance, is very difficult. So rather than getting lost in complex equations and models, a designer uses a extraction tool to get precise values of wire capacitance. If you come to the institute and do the layout with the cadence tool, and after doing the layout, you can do the extraction tool. Resistance and capacitance can be extracted from the layout. You will be able to see the value of the resistance and the symbol also. Okay, so that kind of tool can be used, and it is done. It is done normally instead of going very complex calculation modeling. Consider the first is simple rectangular wire placed above the semiconductor substrate. This is substrate and a rectangular wire with width W and length L is shown here. If the width of the wire is substantially larger, then the thickness is this height H. It may be assumed that electrical field lines are orthogonal, vertical here, as can be shown here. And the capacitance can be modeled as parallel plate capacitance. Okay, but this may not be the case always. Then we have to take it differently. Under those circumstances, the total capacitance of the wire can be modeled as C int. Interconnect capacitance is C int. Interconnect capacitance equals to E epsilon di, dielectric relative permittivity or dielectric constant of the material, dielectric material, that is epsilon 0 epsilon r of that material divided by, this is the thickness of the dielectric material, and this is area. In 130 nanometer CMOS process, you see that fluorosilicate glass FSG with a dielectric constant of 3.6 is used instead of SiO2. Okay, and why it is done? To reduce the capacitor, CW. SiO2 is the dielectric material of choice in integrated circuits, although some materials with lower permittivity and hence lower capacitance are coming in use. And that is what I have shown, that material. Examples of later are organic polyamides and aerogels. Aerogels is very good because its epsilon is very less. Okay, and there will be a table to discuss for that. See, free space relative permittivity is 1, aerogels 1.5, and this organic material polyamides is having 3 to 4, whereas silicon is 3.9. So you can see that compare with this aerogels and silicon dioxide, it is better because capacitance C wire will be less in case of aerogels. Is it understood? Ask the party.
Yes, sir.
The smallest to simplistic to determine the resistance of wires while scaling technology, it is desirable to keep the cross section of the wire W by H as large as possible. On the other hand, small values of W lead to denser wiring and less area overhead. So as a result, we have over the years witnessed a steady reduction in the W by H ratio. W is the width, H is the height or thickness of the wire, so that it has even dropped below unity. Now this ratio is less than unity in the advanced processes. This is clearly visible on the process cross section of figure. Under those circumstances, this parallel plate model assumed above becomes inaccurate. We are discussing that capacitance can be considered, wire capacitance can be considered as parallel plate capacitance, but that may not be possible always because you see its dimension has been reduced a lot. And another kind of capacitance is going to come into effect, that is fringe capacitance. Here is the details about fringe capacitance. Here at the bottom, these field lines are orthogonal to the here ground plane, maybe substrate, but others field line are not perpendicular. So these field lines from the side creates the C fringe capacitance. So in addition to this CPP parallel plate capacitance, you will have to account for this C fringe also. Sorry. And the resulting approximation is simple and works well in practice. C where capacitance or C int, you can say interconnect capacitance equals to CPP plus C fringe, which is given as W epsilon di by T di. plus 2 pi epsilon di y log of TDI by H, where W is given as W means width of the interconnect minus H by 2, where H is the height of the interconnect. A good approximation for the width of the parallel plate capacitor. Now, to illustrate the importance of the fringe field capacitance, see this figure. This figure plots the values of the varying capacitance as a function of W by Ti. Your x-axis is W by Ti, TDI, or indirectly of W by H. For larger values of W by H, the total capacitance process the value allocated value of the capacitance. Okay. For smaller than 1.5, the fringing component becomes dominant. Today's processes offer many more layers of interconnect. As I said, maybe 10, even 10, which are packed quite densely. In this scenario, the assumption that a wire is completely isolated from its surrounding structure is not correct. This is illustrated in this figure. See that this is one metal line. It is surrounded by another one, the right side, at the left side, maybe at the bottom also. Okay, maybe if bottom you don't have anything, another metal line, at least there may be a substrate. Okay, so at the top also you have other metal lines. Okay, and some of them the capacitances are parallel plate capacitance, some are fringe capacitances. So capacitive coupling will be there. Effect of one will be falling on the other one. Some capacitors are floating, some capacitors are grounded, and these capacitances affect the signal level. In other words, creates a noise. Signal wire glitches as large as 80% of the supply voltage will be common due to crosstalk between neighboring wires as features sizes continue to be scaled down. Here you see technology generation. It is 0.35 meter CMOS, 0.25 meter CMOS, and this is 0.16 meter CMOS. So as technology generation is scale down, what is happening? Spike due to pulse. A pulse, clock pulse, for example, in one line is occurring, then its effect on the other line may be like that. As technology is scaling, the spike level is high. A set of typical interconnect capacitances for a standard 0.25 micrometer CMOS processes are given in a table. The table we're going to see now. The process supports one layer of polysilicon. Remember, one layer of polysilicon and 5 layers of aluminum. Which process? 0.25 micrometer CMOS process. It is talking about this. I was telling that today maybe 10 metal layer also, but not this process. This process is having only 5 metal layers and 1 poly. We'll be doing sometimes later, we'll be doing the layout. In that you will have 2 poly, and technology generation is different. When placing the wires over the thick field oxide that is used to isolate the different transistors, use the field columns in the table. We are going to see the table. So it is talking about the what is meaning by field, active, poly, etc., or aluminum 1, 2, 3, 4, 5. So it is telling that if your wire is going to the field oxide, then this column has to be looked at. Okay, this is telling. If you want to see that, if it is going through active layer, then active column has to be seen. To obtain more accurate results for actual structures, complex three-dimensional models should be used, and that take a moment of the wear into account. So this table is telling this is the polylines capacitance. If it is going through field, then this may be the capacitance. This is the parallel plate capacitance. This is fringe capacitance. The gray one is fringe capacitance. Another table is given here. This table tabulates the indicative values of capacitances between parallel wires placed on the same layer. Parallelly, two lines are going in the same metal level. Say metal one line is going, another line is also going parallelly on the same level. For that, it is with a minimum spacing as directed by the design rules. Observe that these numbers include both the parallel plate and fringing. It is together, both capacitances together. The polysilicon wires experience a reduced interwire capacitance due to the smaller thickness of the wires. On the other hand, the thick Al5, that is the top metal layer in this, or top metal layer in 0.25 micrometer process, because it is having altogether 5, Al1 to Al5. So Al5 wires display the highest interwire capacitance because it is wider. First of all, it is wider. Okay, and the oxide is also having higher dielectric constant. It is therefore advisable to either separate wires at this level by an amount that is larger than the minimum allowed, or to use it for a global signals that are not that sensitive to the interference. For example, clock or ground, VDD, etc. This unit is given as autofarad per micrometer for these capacitances. Estimate capacitance. There is an example 4.1 of your book. See that and calculate. Now, what we see is how to calculate the resistance of an interconnect wire. We know that resistance is given by rho L by area A. So rho is resistivity, that is ohm meter or ohm centimeter, and area is what? Height, cross-sectional area, height of the interconnect and width of the interconnect. That gives you area. Okay, which is further written as rho by H gives the RO, or rather it is sheet resistance, so it is denoted by R square. Remember that R1 with the concept of R square or sheet resistance per ohm per square, right? This is equivalent. Same size of you are squaring, it will be having the equivalent. The resistances, resistivities of some commonly used materials are given here, like silver 1.6 into 10⁻⁸ ohm meter, whereas aluminum it is more 2.7. Tungsten is even more. So tungsten is only used for bottommost via, not otherwise. As I said, copper, see, Ag and Au, silver and gold, are costly. Hence, earlier Al was the interconnect material of choice since last 4 decades, not copper, even though its rho is higher than Al. Why? Question is why? The answer will be later on when we'll discuss something else like what? I said what? Electromigration. Since H is a constant for a given technology, thickness of the wire is same in a technology. Say 0.25 micron technology, all the wire thickness will be same. So that is H is same. Similarly, if you take another technology generation, 0.18 micrometer technology, H, whatever H value is there, it will be same for all the layers. So we can write R equals to R square into L by W, or R square equals to rho by H. The sheet resistance of the material having units ohm per square. This expresses that the resistance of a square conductor is independent of its absolute size, as is apparent from this equation 4.4. To obtain the resistance of a wire, simply multiply the sheet resistance by its ratio L by W. Suppose you have a W is the width, L is the length, say 100 is the micrometer length, W is the another W, say 10 micrometer length or width, then L by W will give a number, say 10. So you 10 square. Out of this length, whole length, you are creating a 10 square only. It is possible only 10 square. So multiply R square into 10, you get the resistance. Is it understood? Harsh Tripathi.
Yes.
So sheet resistance for different materials like N or P well diffusion, you have the 1000 to 1500 ohm per square is mean speed type substrate, or NOL it is talking about, because it is lightly doped. N plus P plus, that is for N MOSFET or P MOSFET, sheet resistance is 50 to 100 on 50 ohm per square. N plus A diffusion with silicide, it is 3 to 5 ohm per square. N plus polysilicon without silicide, it is 150 to 200. If it is silicided, then it is 4 to 5. Aluminum, it is 0.05 to 0.1 ohm per square. These are the picture of sheet resistance of different material used in forming the integrated circuit. Now something about siliciding of diffusion as well as polysilicon gate. So it's an alloy. Silicide is nothing but compound material or alloy of silicon and refractory metal like tungsten, titanium, platinum, tantalum, etc. For instance, the WSI2 has a resistivity of 130 micro ohm centimeter resistivity of this, which is approximately 8 times lower than the polysilicon. So if you apply a layer of this material, then altogether resistance will be less. Normally what is done, over the polysilicon, another layer, polysilicon, what is done, say tantalum or WSI2 or TASI layer is applied. What is done actually, it is heated up. The silicon, polysilicon here, not silicon, polysilicon is heated up in the presence of tantalum. Okay, and a alloy is formed. TASI alloy is formed on the top side of the polysilicon. Okay, this is basically polysilicon is what? Basically silicon only. Crystalline structure is polycrystalline. Okay, so a compound material is formed on top of the pure polycrystalline silicon, and its resistivity is reduced 8 times. Resistivity is reduced by 8 times. So with this kind of polycidation, it is called polyciding. Polycidation, you are using the property of polysilicon, which is having very good adherence and coverage and high conductance of tantalum, for example. See, you cannot directly use any material on the gate. On the gate here, for example, here, polysilicon is there on SiO2. This is your insulator on the gate. You cannot make any material here. That material will be good, which is having cohesion property. It will be sticking to that your glass. SiO2 is what? Basically glass kind of material. So some material should be made which is having the adhesion quality. And then this is say tantalum TASI. This will be very good conductor, at least 8 times more than polysilicon. Other things also can be used, like this one, titanium silicide, tungsten, and platinum silicide also. Transitions between routing layers and add extra resistance. Transition between routing layers add extra resistance to a wire, called the contact resistance. We have already discussed something about the contact resistance. Yes or no? Can you remember? Not remembering anything? See, I have drawn in this way, N plus region, okay, on this substrate. So I was showing you that this is also having resistance, and there is a lightly LDD and LDS. It is also having some resistance. It is also having channel resistance. It is also having channel resistance, diffusion resistance, and contact resistance, RC. RC is the contact resistance. This is RC, let me call it RCAs, channel resistance. And this is RD, drain resistance. This is RA, source resistance. And this is RLDD. This is RLDS. This is your source, this is your drain. You have the, did I discuss or not? Tell.
Yes, sir.
So what we are talking about here, the preferred routing strategy is thus to keep signal wires on a single layer whenever possible and to avoid excess contacts or vias. Excess contacts, the contact resistance is there, RC. Okay, so excess contacts should be avoided if possible. It is possible to reduce the contact resistance by making the contact hole larger. Unfortunately, current tends to concentrate around the perimeter in a larger contact hole. We'll see what does it mean about the, say, if you have a circular wire, currents normally will be flowing to the outside periphery of the contact. Same is the case for rectangular Also, we'll see here. This effect is called the current crowding. Current will be crowding
Sir,
around the periphery. Yes.
can we see the rest in the next class? It's past 2. It's past 9.
Okay. Well, next class. So, are you reading this? You are not telling that you have gone through it. Next class on 20th. See, I have to cover the syllabus quickly. So you finish, you are getting a lot of time. So finish these videos so that I can quickly go through.